Good morning and good afternoon, everybody. Welcome to what's now our 15th CFD Build Your IQ session. And today we're going to take a deeper dive into one of the newer features in CFD 2016, and that's the new Solar AEC model. There's a tiny image on the right-hand side which kind of gives you an idea of what we're going to start looking into. Hey, one of you guys needs to be muted. I'm guessing it's you, Todd. There we go. Apologies. So before we get started, the slide deck is going to be available to be downloaded at the link on the screen at the bottom there. It's the same every time, we just increment it up one number each time. So just a little bit about the series for anybody who's new to this and hasn't kind of joined us before. We run CFD sessions monthly. I'm sorry about the background noise, I cannot figure out where it's coming from. So we run these monthly, although the actual help webinar series runs weekly, and we change product every time. So we'll probably talk for about 20 to 30 minutes, and then we can have a bit of a Q&A session, and we can show you the model that we wanted to talk about as well. We've had some really successful webinars in the past. The turbulence model one that Royce ran only a few months back already has had over 10,000 views. And the others are all running at about kind of 2,000. So it seems like, you know, what we're doing is being well received. But if you have any more feedback for us, please feel free to share it. The next CFD session is going to be in a month's time, where we're talking about the new model assessment toolkit, which is the kind of link between CAD and CFD, where we're helping to identify problems with your geometry. As always, once this has been, once we finish today and this is all recorded, we'll upload it to our Autodesk Sim 360 YouTube channel. So feel free to catch up on anything on there. There have been a few knowledge articles that I thought I'd mention, some that seem quite interesting. There's some basics about installing and licensing 2016. There's a new solver in 2016, which is one of the kind of new products we might take a deeper dive into in the future. That's CFD2. At the moment, it has, I'd say, kind of limited capability, so it doesn't apply to all of the different types of analyses we can run. If you click on the link there, that'll tell you what we can do, and it'll give you an idea of the huge kind of speed-ups that you can see without needing to upgrade your hardware. Email notifications for CFD 2015 have been turned off, and there's an article here about how to set them up for 2016. It is very slightly different. We wanted to mention just one final time that there's a change between how you could purchase the simulation products. They used to come under one kind of package, and now moving forwards, they're all going to be separated. So getting down to today's discussion, we've got, I guess, 5 sections. We're going to talk about the benefits of the new solar model over the old, so that's 2015 and back. We've got some new materials, so there's solar windows and walls which only work with this new model. We're going to go into why this has such a massive impact and how it can improve your analyses. A little bit about what CFD is doing in the background. I think it's kind of important to understand how the setup differs, and then we're going to look at a couple of models. I've got one myself, and then Todd has another one to talk about. So the benefits are that we can now more accurately represent radiation as it's transmitted through different media. So that includes glass and walls. We can use more industry standard values, so instead of just using like a conductivity and density like all of our standard materials, now we can apply U values and a solar heat gain coefficient. So they're more kind of industry numbers that you might find on data sheets. Personally, I've found that I've got much shorter run times because we don't need to model a solar dome anymore. So the mesh count is lower, and you get results faster. So in the old 2015 model, when if we had a building with a few windows around the outside, when sunlight hit those windows, they would act like any other material. They wouldn't necessarily pass the radiation through to the other side, and you wouldn't see a pool of light on the floor like you'd expect. They would absorb the energy, and then it would be diffused like a grey body radiation to all of the surrounding parts. So in 2016, we don't do that. The light can pass, the light and the heat and the energy can pass directly through, land on the floor or the furniture or whatever kind of component you happen to have in that pool of light, and it will heat up accordingly. It will also then give off radiation accurately to all the other surrounding parts. And we also don't need an external solar dome, as I mentioned before, and I'll cover how to set that up in a second. So the two new materials, I want to just quickly show how they're implemented. So if I select, this is the building that we're going to talk about in a second, if I select my new solar window, you'll see in my default materials, down the bottom, we have window solar and a wall as well. If I just edit one of those, now under transmissivity, instead of just having a single value which used to range between 0 and 1, we now have a solar heat gain coefficient and a U factor. And these override the conductivity and emissivity in the material. So the solar heat gain coefficient is similar to a transmissivity. It's again between 0 and 1, and it tells CFD how much of the radiative energy can pass through the transparent media. And the U factor, Todd's going to go into this in a bit more detail in a second, but that really is a kind of industry standard value, often acquired through test, and it can account for multi-layered walls, and it also accounts for all three different modes of heat transportation, so conduction, convection, and radiation. I think it's important to mention as well, just looking at the values at the bottom there, the solar heat gain coefficient of a window has to be between 0 and 1. If it's 1, then you don't need a window because all of the energy is going to pass through. And the solar wall has to be 0 because it shouldn't let any light through. Okay, so at this point, I'm just going to hand over to Todd, who's going to talk you through the next section. I think, Todd, you're possibly muted.
I just unmuted myself, so I'm in. So one of the things that I really wanted to dive into a little bit more, what is a U factor? I think a lot of people on the call probably know, but just to make sure that it's relatively understood, it's actually the thermal conductance, and it's the inverse of a thermal resistance. What we can do with the U factor is essentially characterize everything into being a simple block, or a you can reduce some complexity out of a model. If you look at the picture on the top right, what we have drawn is just the interior of an AEC space, and instead of having a window and the exterior air, we can drop that down into being a single U value. Manufacturers will typically provide the value. There's different values for double pane and triple pane windows and different kinds of walls. You may run into an example where you actually need to calculate that U value, and that's what you would use for your the U value that you put into our solar wall. And essentially it's just 1 over the sum of the resistances, so it can be as complex of a wall as you may have. This is also documented further. If you want to look at the example that I have shown here on the right, in the Intro to AEC for CFD, walk through actually replacing a brick wall with an effective U value for the brick wall and the film coefficient that was essentially the exterior heat transfer to the air anyway. I don't know if a lot of people have seen this stuff. It's out there, and it's on the Tech Academy. On this page, we also talk about some other things for simplifying other models, where you can, basically break down an effective conductivity for a wall and try and simplify your models, because having all of the beams and studs and insulation, everything that's involved in a typical building, isn't necessary for CFD. So trying to make it simpler so that you can run faster. Some of this translates over. The software will actually automatically calculate your effective conductivity, which I believe John will go into in a couple minutes here. All right, John, I'll pass it back to you.
Thanks, Todd. So I guess for almost all of us, what we found before was that because we weren't kind of transmitting the energy correctly through the windows, we weren't necessarily hitting the correct figures within the building. It was often very close, because we still had the correct amount of energy entering, but it wasn't necessarily being directed to the right places. So this is the kind of big game changer that as we see it, we can really kind of direct that now, and you can see on the left-hand side that's a ray trace of the model, and on the right-hand side, CFD's replicating the same results. So some of what's going on in the background, I kind of wanted to explain a bit of this because you do set the model up very slightly differently. But just to mention first, we can have multiple obstructions. So you could have like a zigzag kind of window shape. You could have multiple panes or even internal windows. And the solar energy will be attenuated by each layer of glass that you reach. And we can use this U factor for walls and windows, which is kind of useful. As I said before, we don't use the conductivity within the material anymore, which is okay because CFD looks at the thickness of the material and multiplies that by the U factor, and that gives us an equivalent conductivity. So we're still using the manufacturer's data and your CAD geometry. So if you change your CAD geometry, the equivalent conductivity would be different. And there's no need to model a solar dome anymore, as I said, I think 3 times now, which is great because it's a massive changer for me. It makes things run much faster. So CFD, I'm going to actually jump to CFD just to explain how this works. So when we actually get to the solar heating section, we enter a reference temperature. So what CFD will do is hold all of the external walls fixed at this temperature. So if we take a look at the results, and I'll basically show everything, you can see that all of my walls are fixed at 10 degrees C. And that may be a good thing, that might not be a good thing. It depends on the type of setup that you want. If you would like more control over that, that's fine. You can simply apply film coefficients to the walls, and then we can allow some heat to escape. While we're here, what I thought I'd also mention is that you can float over any of the solar walls or windows. You can check the the U factor is correct, and that what we would have done is taken the thickness from your CAD and multiplied them together to get that equivalent conductivity value. Okay, so just switching back to the presentation. I think I said before we can have any internal walls and windows. All of that is okay, and it should, yeah, and we will still allow radiation to pass through those within a building. The existing radiation model still works, so anything that gets heated up within the structure, if it isn't a solar material, it will heat up correctly, and then using the original radiation model, it will heat up the surrounding components. So just to take a kind of graphical look at the changes and how they've affected the results moving forward. On the left-hand side here, we've got the CFD 2015 model. So this would be with a solar dome, and this is what the results look like. So this is just looking at solar flux, and what's correct is the solar flux on the outside of the building, so you can see where the sun is going to be on the right hand side, and we've got the cooler side on the left. What is different and not quite accurate, I would say, on the bottom left is that we haven't got this solar flux passing through the glass and not heating the internals up according to kind of how we would expect. We'll take a look at temperatures in a second, so you can see that the results are still good, but they're not as good as with 2016. So I did two other things as well. With the central images, I ran the same model in 2016 with a solar dome. Now you can see that the glass is blue, so there's no solar load on them. It passes directly through, and you can see that it's applied to the walls and the floor internally. And then I ran the model the newest way we possibly can with no solar dome. So there's obviously no solar loading outside. Everything is drawn straight through and passes into the central section, but we're still getting the same internal results. So it just kind of demonstrates that we don't need the solar dome anymore. Just to take a look at temperatures, same thing as before. So on the left we've got CFD 2015. And if you compare the bottom left and the bottom central images, that's the internal structure with 2015 and 2016 with the exact same setup. So the results are pretty similar. We're still warming the air up inside, but we're warming it up slightly differently with 2016, slightly more accurately. So the results should be a bit better. The thermal comfort will be more accurate because the heat distribution is going to be more representative of reality. And then on the far right, we've done away with the solar dome. So again, the external temperatures are absolutely fixed at 10 degrees C because we didn't apply a film coefficient in this case. But again, the internal temperatures are going to be pretty representative of reality. So since this has been released, we've had quite a few cases asking about it, so it's great that customers seem to be using this, which is excellent. We've run a few test models and we've learned quite a lot as we went, so I thought I'd share just a couple of slides of just tips and recommendations. The first one, to me, I think applies to every single model that we run. More mesh is generally a good thing. And I just wanted to demonstrate that here. So we can see that along the top of the top line there, that's just a very standard automated mesh. And if we take a refined mesh, we can see that the way the solar radiation is loaded onto the walls and the floor is going to be slightly more accurate. We don't need to worry, like with resistance regions and that kind of thing, about refining the glass. I spoke to the developer about this too, and he said that the glass can just be pretty coarse. That's fine. It's where the radiation is going to hit the surfaces, the solid surfaces, that we want to have a nice refined mesh. If we're going to run transient solutions, we can use the automatic inner iterations flag again. I did start to mess around with some transient solutions with this, and the flag's really useful. So it basically will allow CFD to just essentially ditch any inner iterations that it doesn't need. So if you might set 3 inner iterations, and if after the second one nothing's changing, CFD will just move on to the next major time step. I said before, but I think it's worth repeating, that we don't use the material conductivity now. So if you're running these analyses and you're starting to tweak the material conductivity to affect the results, nothing is going to change. Only the U value and the thickness of the material will change the effective conductivity of each part. We don't use the emissivity, we use the solar heat gain coefficient instead. And although an external film coefficient isn't required, you're more than welcome to apply one, and I wanted to just show with the same model without a solar dome what the results can look like. So internally they're going to be very, very similar, but on the right hand side I did apply film coefficient to the external walls, so we can see that we're starting to draw some heat out, which might again take you a further step towards really accurate results. I think that pretty much covers everything I wanted to talk about. I'm just going to pass you back to Todd now, who's going to talk about the model that he ran.
All right, guys. I decided I was going to taking some time away from the webinar, so for my return, I figured I'd go medieval on you. Couple of things that I noticed while I had just gone through to set it up. I wanted people to avoid some of the simple errors that you can run into. even if you're trying to get rid of the dome and run the analysis, if you don't have the solar materials, what will end up happening is heat transfer will get turned off, and you'll end up with all of your temperatures being at the exact temperature that you had for your reference temperature for the solar. So we need to use those in either case, whether we have the dome or not. If we want to have that pass-through, if we're getting rid of the dome, it's absolutely necessary, or heat transfer just won't run. Let me snag over control here. Oop. And show my monitor. Hopefully that's coming up for you. So here, just to walk through what I did, I've got my concrete castle, and I threw on a couple of solar walls, and I decided why not have some nice sliding glass doors, and then another window
Hey, Todd,
on the back of our... What's that?
I think you might be sharing the wrong screen. I can see a dog, which is kind of cute, but
Oh, you got Leroy?
yeah, we got
I
Leroy.
don't know why that didn't go to the other monitor. Let me switch. I don't know why that happened.
It's just any excuse to show pictures of your dog, I know.
All right, you know, he's a good one. He doesn't know too much CFD though. So anyway, back to here's the model that I have, a little castle, and have a couple of solar walls that won't really let through any flow or any solar energy. But then I decided we should have some sliding glass doors into our penthouse and another window off the back.
Sorry, Todd. The screen is black. There's nothing coming through other than that.
Nothing is coming.
No, so perhaps it's better to...
Maybe I'll go over to the big screen and try and share back where you had Leroy. I don't know. Anything coming through?
I'll let you know. Yep, there you go.
Okay.
Thank you.
So yeah, I'm not sure why that wasn't working for you guys before, but here we go. Now you can see my castle model. Again, here are my solar walls, and then I decided we needed to have our window on the back and a little screen there. These are all the solar windows. I deselect all. You can see that that's what that was. And John had already walked through the setup. I think I had made it turn on your heat transfer, your radiation. You'll most likely want gravity, and change on your solar heating. I use 20 Celsius as my reference temperature. And this actually has a fairly poor mesh, but really all we're looking at is our top room, and you can see I've got an ISO surface with temperature showing here. So we can see that actually as I heat up the floor from the sun coming in through both the glass door over here and this window, I actually start to have some hot air rising and filling out. We have no real ventilation, so it kind of just gets stuck in there. But I thought it was a fun model to show, just to give a reasonable representation of what can happen. And I've run this a few different ways. Like I showed you guys, where if you don't have the new solar materials, your results will be either representing similar to 2015, where we'll do the complete gray body diffusion, or if you're doing it without the exterior air domain, it'll drop it down and just give you your reference temperature everywhere. The best way, John had shown you guys using some film coefficients on the outside to show better what the heat load might be. The best way to truly get the heat load shown on the exterior is to still have the dome. So it really just depends on what you need out of the analysis. Talked to some customers that just having it on the inside is enough, and then absolutely get rid of all the mesh for a dome. My dome is not appropriately sized, so you'll end up with a massive runtime. The larger it gets, the more elements you're going to use. And I think that's all I really wanted to point out and talk to you guys about. Looking at some random different results here. At that point, I guess, do we have any questions we should be addressing?
Yes, so far, I think we've just got one. I have a case with the same guy. Hey, you pal. Basically, the customer has a problem where he's got 3 kind of layered walls within Revit and a reflective paint on the outside of the building. And what he's trying to do is represent all of that with the new model. And I'd see if you agree with me, Todd, but I think, you know, especially using the new data that we have on the how to calculate the U-values, you know, by summing up all the resistances and using the reciprocal, that we should be able to model all of that with a single wall. And if we tweak the, yeah, I'm not sure. What do you think? I was thinking about
you should be able to drive that all. You know, you wouldn't need to have multiple solar wall types. You should be able to calculate that down to being one solar wall.
The problem I see, though, that I guess I didn't think about before, I think it needs to kind of be 2, because we have a 0 solar heat gain coefficient right with the solar wall, so we're always absorbing all of the energy. But if we're actually if we've got an 85% reflective wall and we really want to only absorb 15%, then I think what we need to do is have 2 sections. So we'd have like a solid inside. We could use a solar wall, that would be okay. To use the U value of the combined 3 layers, or just calculate an average conductivity using the thicknesses, and then have a solar wall on the outside as well, so we could then take the solar heat gain coefficient to tweak the reflectivity. Then we could use a new model. Yeah, I don't know. I think that answers the question for me. Does that make sense?
I think so. I don't know.
Okay, it's just you and me talking, so.
Right.
Yeah, let us know, Yuval, if that is useful to you or not. At the moment, though, there are no other questions. Does anybody have anything else that they want to ask about the new model? Okay, I guess not so much right now, which is really cool.
Either we're going to get beat on for it later, or we did a good job explaining the new stuff.
Yeah, I think it's pretty straightforward.
Yeah.
I mean, the real basics are remove the solar dome, assign solar walls, solar windows with correct solar heat gain coefficients and U values, and then either apply a film coefficient or use the ambient reference within the solar heating dialog. That's pretty much it. It seems to work really, really well.
Yeah, I'm fairly pleased with being able to see some of that, because it's definitely a huge difference when it comes into human comfort. Just because if you've got a guy standing by a window, previously we could say that he was the same as the rest of the room, which when you had your temperatures showing on, oh, if I have that, I don't have the slideshow open at the moment. I go back, this one? No. Couple down.
Which are you trying to find there, Todd?
I was just looking for the, when we were looking at the internal surface temperatures.
Okay.
Which I don't think this is the same picture. I think you actually replaced them once you got the legends to be the same.
Yeah, that's right. So
the back wall was very hot. Do you want to take over as presenter and show that slide?
Yep. I'm getting there. Right, that should be visible now. Let me know if you can see my screen okay. And then feel free to explain away. I wasn't sure what you were going to say.
Screen hasn't shown up yet, but maybe we're on the same delay. Takes a little while for the complete presentation to pass. Maybe not.
No, I think we're good now.
Oh, there it goes.
Cool.
Make that bigger. But if you look at the bottom left-hand picture, you see that that whole back wall is hot. And in general, a lot of the internal room is going to be shown as a different temperature than actual in reality, because you would have pretty decent hot spots right where the windows are going to shine in, which we're showing in 2016 there. And it's going to reduce the overall room temperature and have a higher local spot. And that can be very impactful if you're considering where someone's going to be in a room. Because, yeah, you can take a beating from the sunlight in a corner, or previously if we had something that was just a room that had a lot of windows around it, maybe you would get very hot, and that could be something you may want to consider while you're doing an HVAC layout or anything like that, because if you're not properly cooling that corner of the room, the solar light is going to give people a sunburn, and it's going to be just too warm.
Yep, I agree, Todd. That's, I guess, why it's going to be so useful moving forward. It does seem to have a nice kind of jump up in accuracy, which is smart.
Yeah. Yeah, it's absolutely, and just I thought that picture showed it pretty well, and wanted to at least kick it out there in a different sentence, just so people might see it a little bit better.
Cool. Perfect. Okay, I guess if there's no other questions at this time, so type quickly if you'd like to ask one. Otherwise, I think we'll wrap it up there. We've covered the basics, and I think that's sufficient. Todd, agree?
Yep. Yeah, I think no sense in dabbling in everybody. We can give you back the rest of your day.
Perfect. Well, thank you for joining us, everybody, and feel free to join us next week for a different product, or in a month's time for the next CFD session. Have a nice day.